Okay, in this video, we're going to look at how to determine the hybridization of atoms in some certain compound. So here, what is the hybridization of carbon in carbon dioxide? What is the hybridization of carbon in carbon dioxide? So we are to determine the hybridization of carbon in what? In carbon dioxide, which is CO2, right? So carbon is the number 6 element in the periodic table, and so it has 6 electrons. Oxygen is the number 8 element in the periodic table, and so it has 8 electrons, right? So if we are to draw out the configuration of carbon, this is carbon. The innermost shell will take a maximum of 2 electrons. These are the 2 electrons, and then we have 2, 1, 2, 3, 4, 5, 6, right? So this is carbon. This is carbon having 6 electrons. 1, 2, 3, 4, 5, 6. And then we'll draw oxygen. This is oxygen. We'll have 2 electrons here. So 1, 2, 3, 4, 5, 6, 7, 8, right? So this is oxygen atom. This is carbon atom. So this is oxygen having 8 electrons, right? So we have to draw another oxygen atom because in carbon dioxide we have 2 oxygen atom and 1 carbon atom, right? So this is another oxygen. 1, 2, 3, 4, 5, 6, 7, 8, right? So these are what? The 8 electrons in oxygen. So this is oxygen atom. So we're looking for the hybridization of carbon in carbon dioxide. So one thing you must remember is that hybridization of an atom depends on the regions of electron density around that atom. So the hybridization of carbon in this compound depends on the region of electron density, the regions of electron density or concentration around this carbon atom. So during chemical bonding, this electron from this carbon will bind with this electron from this oxygen. This electron from this carbon will bind with this electron from this oxygen to form a double bond. This electron from this same carbon will bind with this electron from this oxygen. This electron from this carbon will bind with this electron from this oxygen to form another double bond. So the electron density around this carbon atom are actually 2 double bonds. So in this compound, there are 2 carbon to oxygen double bond, and that is equivalent to 2 regions of electron density. Let me represent that as ED. 2 regions of electron density, and 2 regions of electron density is equal to the sp hybridization. So the hybridization of carbon in this compound is sp hybridization, and the bond angle around this carbon atom, the bond angle will be what? The bond angle will be 180 degrees. The bond angle is 180 degrees, and that the shape of the molecule, the shape will be what? Will be linear, right? So that is how to look for the hybridization of carbon in carbon dioxide. So having done that, let's look at what is the hybridization of oxygen in carbon dioxide. So here we looked at the hybridization of carbon in carbon dioxide. Here we're looking at the hybridization of oxygen in carbon dioxide. So we're looking for the hybridization of oxygen O in what? Carbon dioxide. So again, this is oxygen atom, this is carbon, this is oxygen, right? So we are considering oxygen here. We are looking for the hybridization of oxygen in carbon dioxide, right? So we are considering one of the oxygen. We can consider this. We can also consider this oxygen. So let's go with this oxygen, right? So in this oxygen atom, we have two lone pair of electrons. This is a lone pair of electron, a lone pair. This is a lone pair of what? Of electrons. So a lone pair of electron is when you have two electrons that are not involved in chemical bonding, right? They are not involved in binding with other atoms to form a molecule. So this is a lone pair of electrons. It is not involved in chemical bonding. When you have two electrons that are not involved in chemical bonding, that is a lone pair of electrons. So this is another lone pair of electron, right? So this oxygen has two lone pair of electrons, right? Remember, hybridization depends on the regions of electron density around an atom. So we are considering this oxygen. We are looking at the regions of electron density around this oxygen atom. So we have two regions of what? Electron density. We have two lone pairs of electrons. So these two lone pair, these two lone pair of electrons is equal to what? Two regions of what? Of electron density, ED, right? So we have two lone pair of electrons. This is a lone pair of electrons. This is another lone pair of electrons, making it two lone pair of what? Electrons. And that is equal to two regions of electron density. Then we have this electron from this oxygen binding with this electron from this carbon, this electron from this oxygen, this same oxygen binding with this, with an electron from this same carbon to form a double bond, right? So there is one carbon to oxygen dot double bond, and that is equal to one region, that is equivalent to one region of what? Electron density. So if we add these two regions, we have 2 plus 1, that would be what? 3 regions. So we have a total of 3 regions of what? 3 regions of electron density, of ED. And that is equivalent to the sp2 hybridization. That means two of the p orbitals is mixed with what? An s orbital. So that is equivalent to 3 regions. So that is what? sp2 hybridization. And the bond angle will be 120 degrees. So the bond angle around the oxygen will be 120 degrees, and that will give the shape to be what? Trigonal planar. That will make the shape to be trigonal planar, right? So that's the hybridization of oxygen in carbon dioxide. So the hybridization of oxygen in carbon dioxide is sp2 hybridization. The hybridization of carbon in carbon dioxide is sp hybridization. Let's look at the hybridization of oxygen in water. So here we're looking at the hybridization of oxygen in what? In water, which is H2O. So first of all, I will have to draw the structure of the oxygen, right? So this is oxygen having 8 electrons. It is the number 8 element in the periodic table, and so it will have 8 electrons, right? So this is 1, 2, 3, 4, 5, 6, right? So this is 1, 2, 3, 4, 5, 6, 7, 8. These are the 8 electrons in what? Oxygen. Then we have hydrogen. Is the number 1 element in the periodic table, and so it will have just 1 electron. So this is hydrogen, 1 electron. This is hydrogen, 1 electron. So this is hydrogen, and this is what? Oxygen, right? So we're looking at the hybridization of oxygen in what? Water. So like I said before, hybridization depends on the regions of electron density around an atom. So the hybridization of oxygen here is solely dependent on the regions of electron density around this oxygen. So in this oxygen atom, we have two lone pair of electrons. This is a lone pair of electrons. This is another lone pair of electrons. Like I said, a lone pair of electrons is when you have two electrons that are not involved in chemical bonding, right? So we have in this oxygen, we have two lone two lone pair of what? Electrons. And these two lone pair of electrons is equal to two regions of what? Of electron density. Then during chemical bonding, this electron from this oxygen would bind with this hydrogen. This electron from this oxygen would bind with the electron from this hydrogen. So in this compound, we have two oxygen to hydrogen what? Single bond. This is a single bond. This is another single bond to a hydrogen atom. This is a single bond to a hydrogen atom. So we have two oxygen to what? Hydrogen single bond. And that is equal to two regions of what? Electron density. So if we add this up, that will give us a total of four regions of what? Of electron density. And that is equal to the sp3 hybridization. Three of the p orbitals and what? S. So that will give rise to what? sp3 hybridization. And that will make the bond angle around the oxygen to be what? To be 109.5 degrees. That will make the shape to be what? The shape of the molecule to be tetrahedral, right? So that is how to look for hybridization in inorganic compounds or